Hi ladies, so we're going to have a go at a few bond energy questions and Hess's law questions. I know we went over the definitions yesterday and there's quite a few of them to learn off, but the maths bits I don't think are too hard, but we'll give them a go and see how you get on, okay? So first of all, we're going to look at bond energy questions. These are the ones that are less likely to come up, they're less common, okay? So I'm only going to do one example of this and I might give you one if I can find an example online as well. Okay, so essentially you're given an equation, okay? Now just remember, these little things in the brackets after the reactants and products are only the state symbols. They're telling you whether something's a gas or a liquid. All of these things here are gases, okay? And then you were asked to calculate the overall enthalpy or overall heat change for this reaction here, given that the bond energies for the following are, okay? So your oxygen double bond 498, C oxygen single bond 358, and so on here. Okay, so these are the bond enthalpies. Okay, so remember, the important thing to remember here, girls, is that to break a bond is an endothermic reaction that takes energy. That kind of makes sense. To break something will take energy. You have to use your muscles. Okay, to make something is going to release energy, so that's going to be an exothermic reaction. So remember, endothermic reactions, girls, will have a positive delta H. Exothermic reactions will have a negative delta H. Okay, so hopefully that's clear. Now what we're going to do is we're going to look at this equation and we're going to draw out the molecules and work out how many bonds are made and how many bonds are broken in this experiment, and then look at the overall energy change. Okay, so looking off at the reactants first of all. So your reactants, we've got methane here. Methane is made of 4 carbon-hydrogen bonds. If we're breaking, because remember these are the reactants, so we have to break up the reactants before we make the products. So if we're breaking up each one of these bonds, it's going to take energy. So therefore, we are breaking 4 carbon-hydrogen bonds. Therefore, it's 4 multiplied by positive 413. That's what we were given at the start of the question. It's positive because it's breaking the bond. It's an endothermic reaction. So the overall change, energy change for that is positive 1652. So it takes 1652 kilojoules per mole to do that, okay? Our other reactant there, girls, is breaking 2 oxygen double bonds, okay? So again, you're multiplying 2 by positive 498. Remember, it's positive because we're breaking them, and overall energy change is plus 996 kilojoules per mole. That's our reactants. Now we have to look at our products here, girls, okay? So our two products are carbon dioxide. We're making 2 of these bonds here because there's 2 C double bond O bonds. Remember, when you're making things, it's an exothermic change. So you multiply 2 by the enthalpy change, or the enthalpy for a C double bond O bond, and remember it's negative because we're making them this time. It's giving it energy, so your overall enthalpy change there is minus 1464 kilojoules per mole. And then we're also making 2 water molecules. So that means we've got 1, 2, 3, 4 HO bonds, okay? So 4 multiplied by minus 463, that was given at the start of the question. It's minus because we're making the bonds, so therefore it's an exothermic reaction. So the overall heat change for this is minus 1852. Now we're here, girls, we're working out, we're working out our overall enthalpy change. So what we have to do is we have to add up the heat changes for our reactants and the heat changes for our products. So what we're doing is we're simply just adding all these things together. So it's positive 1652, positive, that's for your methane, breaking your methane bonds, positive 996, that's for breaking the oxygen double bonds, okay? And then we are negative, now we're into our reactants, our products, so we've made these bonds, 1464, that is for the making of your carbon dioxide bonds there, and then minus 1852 for making your 2 water molecules. So we add up all of these guys and we work out what the overall heat change is. So where is my calculator on? That'll be another thing, Okay. So you add these up, so it's going to be 1652 plus 996 minus 1464 minus 1852. Okay, so your overall is minus 668 kilojoules per mole. So that is your overall enthalpy change, your overall heat change for that reaction. So that is your answer there, girls. So hopefully that is clear enough. All right. So I'll try and find another question that you guys can have a go at yourselves based on that. All right. Now, next question is your Hess's law question. So remember, Hess's law is all about working out what the heat change or enthalpy change for a reaction is based on a number of different steps, okay? So this question here is asking us to work out what is the overall heat change for when carbon, which is a solid in its form graphite, because remember carbon's a bit of a complicated material because it can be graphite or diamond. So what's the heat change required for the solid graphite to change into the solid diamond, okay? So we are given the following information to be able to work that out. That carbon, when it's burnt with oxygen, gives carbon dioxide as a graphite. There's our overall heat change there. Hopefully you can see that at the end. There you go. Okay, and we're also given carbon in the form of diamond, also burnt with oxygen, forms carbon dioxide, and that's the heat change there. Okay, now what we have to do is we have to try, it's a bit mathsy, rearrange these guys and add them up in such a way to be able to make this equation here. Okay, so let's look at this. So we have carbon graphite on this side of the equation. Okay, here we've got carbon graphite here. So this equation is going to stay as it is. Okay, so we're going to write this as it is. So CS, and I'll just write graphite here, okay, plus O2, arrow CO2, which is a gas, okay, and your delta H there is just as it's written there, minus 393.5, okay. Now, so that's the first step done. Next step, girls, you have to look at, we've got carbon as diamond on this side of the equation, whereas where we want it is we want it on the other side. So what we're going to do is we're going to invert the second equation, and if we invert it or we've changed the order of it, so if you make this side the products instead of the reactants, we have to then change the sign of our delta H to positive. Okay, so that's what we're going to do here. So it's going to be CO2 gas, arrow, forms O2 plus carbon solid diamond. So we've just switched that equation around, and our delta H now has changed sign to positive 395.4 kilojoules per mole. Okay, that one's kilojoules per mole as well, okay? Okay, so that's what we've done, all right? So now what you're going to do, girls, is you're simply going to add these equations up, and you should get the overall equation here at the start, okay? So let's add these up. So if anything appears on opposite sides of the equation, we can just cancel them off, okay? So here we can see oxygen is on this side of the arrow, the product side. On the above one, it's on the reactant side, so we just cancel those off. Is there anything else that appears on opposite sides of the arrow? Yes, carbon dioxide can be cancelled off, carbon dioxide can be cancelled off. So now we just add up what's left. So C, solid graphite, okay, arrow, C, S, diamond. Okay, and so that's the equation, exactly the equation that we're looking for at the start. Now what we have to do is we have to add up our delta H's here. So it's going to be 395.4 minus 393.5. So that is, your answer is 1.9 kilojoules per mole. That's your answer there. That's the overall change for that heat change for that reaction there. Okay, so that's problem one. Problem two that I showed at the end of the last video. So problem two, girls, we are trying to create this equation from these two equations here. So let's have a little look. So we've got 2 NOCl. So 2 NOCl we can see is on this side of this equation here. So that's on your product side. So we're going to have to invert this equation first. So let's invert this and change this sign of the delta H. So 2 NOCl, arrow Cl2 gas, sorry I forgot my state symbols there, gas, plus O2 gas plus N2 gas, okay, and our delta H there is going to be opposite sign there, so minus 103.4. all right, so that's the first step done there. So I have this on the right side. Now what I want is I want my 2NO here on the opposite side here, okay, just here in this equation here. So I'm going to have to invert this one here as well. So that means I'm going to have N2 plus gas plus O2 gas, arrow, 2NO gas, okay, and your delta H then has to be changed, its sign has to be changed as well, so that's positive 180.6 kilojoules per mole. I keep forgetting to write in my units, sorry girls. Okay, now, so let's look at this here again. Now, so I have my start material on the right side, I have my product on the right side. Now we're going to have to see if anything cancels out, if there's anything both sides of the arrow. So you've got N2 on this side and N2 on that side, so I cancel these off. N2's gone, N2's gone. What else? I've got O2 on this side, I've got O2 on the other side of the arrow there as well. Okay, so now I think we can add it up. So it's 2NOCl, gas, arrow, goes to goes to 2NO gas plus Cl2. So that's exactly the equation that I am looking for. Okay, so it's exactly the equation I'm looking for. So now what I'm going to have to do, excuse me. So now what I'm going to have to do is I'm going to have to add up my delta H's here. Okay, so I have to add up my delta H's. So it's going to be minus 103.4 plus 180.6. Okay, let me see if I've done that right. So minus 103.4 plus 180.6. Okay, your answer is delta H is equal to 77.2 kilojoules per mole. That's the overall heat change for that reaction then, okay? And I'll do the third question now in a second. Okay, close. Okay, now, all right, so that's our second question there. Now our third question, our third problem there, ladies, is there. Okay, so we have to try again and make up this equation from these two equations given to us. So our N2 is on the right side here, that's okay. Our 2NO2 should be on the product side, so we're going to have to invert the second equation. So it's going to be pretty standard, N2 plus, which is a gas, plus O2 gas, arrow 2NO gas. That's delta H, you don't need to change anything there, plus 180 kilojoules per mole. And then the other one we're going to have to invert, so it's going to be O2 plus 2NO, I keep forgetting my state symbol, sorry, gas, arrow goes to 2NO2 gas, and we have to change the sign for this second equation because we've inverted it, is equal to minus 112 kilojoules per mole. Okay, now so let's see if anything appears on both sides of this equation. So we've got 2NO gas can be cancelled out, and we've got what else is there? I think that's all that can be cancelled out here, so we just have to add up the rest. So it's going to be N2 gas plus 2O2, because you've got O2 here and O2 here. Arrow goes to 2NO2 gas. So you can see here that we've made the reaction that we wanted to originally make. Now we have to add up our delta H's to get the overall heat change. So it's going to be 180 minus 112, and that the answer there, girls, is 68 kilojoules per mole. Okay, so there's your answer there. So hopefully you're kind of starting to see a trend here in how these work. I'll post up some extra examples and ones that I want you to try tomorrow.